little bit of a song called All Thumbs, recorded by the great Chet Atkins. All right, so what we will be doing in this section in Calc 2 is looking at integration of finding volumes by three different methods. We're going to be kind of looking at a general slicing method, a disk method for solids of revolution, and a washer method for solids of revolution. So to begin with, we're going to look at a general slicing and dicing method here. Okay, so to begin with, I've got a diagram here. I'm going to go ahead and go through this example right here. And what we're looking at primarily is if we have some object that's extending from x equals a to x equals b, we're looking at some sort of a solid that can be represented by this integral where a represents an area of the cross-section. So a good way to explain this will be an example kind of like this. I'm looking at, to begin with here, a quadratic y equals 1 minus x squared, kind of like this. And we're going to have a solid that has a base that's perpendicular to the base and parallel to the y-axis. Those are squares. So the diagram shows this pretty well. We're going to be looking at 1 minus x squared. Now see, this is the positive x-axis here. And then we have the positive y-axis like this. Okay, so that's the positive y-axis like here. So really this area right here is quadrant 1. I'm kind of laying that down flat so you can see the three dimensions well. So what we're doing on this is we're going to be integrating squares from 0, 0 out to this point right here, whatever that point is right there. And we're going to be doing cross sections of squares, kind of like that then. Okay, so to begin with, we're going to be integrating these square regions right here. So I'm going to draw, you can kind of see this square at the end like this. So that's going to represent a square. We know that all sides are equal in a square. So we're going to have something like that. Then another situation would be, here's a square that kind of goes through like this. All right, so what I'm saying on this is we got squares. You can see I've kind of highlighted a square here. So let's say we have some point on this quadratic, and then we're going to kind of dash that to the x-axis, and then we're going to go up so that this is the same shape, or same dimension like this, and we're going to have a bunch of squares that we're going to be integrating from 0, 0, until we get out to, say, this point right here. So once we get to that point, then we'll complete our integration. So what we want to look at to begin with is, what are these sides? Okay, this side of the square right here is given by whatever f of x is. Okay, technically it's given by, that dimension would be f of x minus 0, because it would be the curve defined by the quadratic minus the x-axis, okay? And then this dimension right here would end up being exactly the same because it's a square. So we have f of x by f of x like that. Okay, so one of the things that we're going to have, if I was to go through and just draw a shape, like I'm going to do here kind of at the side, like if we have a square, kind of like I'm drawing there, okay, well the dimensions on this are going to go like this. Since the dimensions are equal in a square, this is going to be represented by f of x, which is 1 minus x squared. This is also going to be the same. That's going to be represented by f of x equals 1 minus x squared like that. So what we have for our area function is the area is just base times height. So it's going to be those two things multiplied. So we'll get our area function is going to end up being 1 minus x squared, the base, times the height, 1 minus x squared. So that's going to be equal to 1 minus x squared squared. So that's what we're going to end up integrating, is we're going to integrate that area function right there. So what I'm saying on this is, in this formula, that's your area function right there. That's what's going to be 1 minus x squared squared like that. And then dx, what that represents is the thinness of this square. Okay, so just kind of imagine a little slab like that. Dx is this little edge right here. Okay, so that's how thick that square is because we're doing a volume. Okay, so now we're going to set up our integral, and we're going to integrate and find that volume now. Okay, so what I'm going to have then is I'm going to have the area, or the volume function is going to be equal to the integral from a to b. We've got to figure out that intersection point, and then we're going to integrate 1 minus x squared squared times dx like that. Now we've got to figure out that intersection point, which is really just an x-intercept. So if we want to find an x-intercept, we're going to take the function that we're working with, which is this, and we're going to set that equal to 0. And of course that would be 1 equals x squared. You would take square root of both sides, so you would have 1 is equal to, or x is equal to plus or minus 1. So that means this point right here has an x value of 1 and a y value of 0. So what we're going to do is we're going to integrate from 0 to 1. Okay, like that, and then that will give us the value of this volume then. Okay, so that's basically what we're going to do to get that volume. Okay, so we got everything that we're ready now to do our work with our integral now. So we're going to go ahead and work this out. I'm going to go ahead and multiply this out. I can FOIL that, so that's going to be 1 minus 2x squared plus x to the 4th times dx. If you FOIL that, you can write that out twice and FOIL that. You know, the shortcut that you do on this too, by the way, is you go square the first term. So you do 1 squared, you square the last term. Okay, then you multiply those together to get negative x squared, but then you double it. So what you get is 1, and then this becomes minus 2x squared after you double it, and that becomes plus x to the 4th like that. So that's one of the things that you want to be able to do. Now this is a basic power rule integral, so we can do that. Okay, so I'm going to go ahead and get the antiderivative. So that's going to be antiderivative of 1 is x. Then power rule here, we're going to have 2 times x to the 3rd over 3, and then plus x to the 5th over 5. And we're going to evaluate that from 0 to 1 then. Okay, so then when we're doing this, we're going to go ahead and just work out the arithmetic. So we're going to have 1 plus 2 times 1 to the 3rd over 3 plus 1 to the 5th over 5. And then we're going to plug in the 0. So we'll have 0 plus 2 times 0 to the 3rd over 3 plus 0 to the 5th over 5. And then we'll crunch out the details of the arithmetic. And then we'll have a conclusion on this then. Okay, so this is going to be 1 plus 2/3 plus 1/5 there. All this over here is going to be 0. You just have 0 plus 0 plus 0. So we end up just adding these fractions. They have a common denominator of 15, so I'm going to write that as 15 over 15. I'm going to multiply this by 5 over 5, and then that will give 10/15, like that. And then I can multiply the next one by 3 over 3 to get 3/15. So I would get a final result on this of 28 over 15 should be the final answer to the volume. Okay, like that. So that's the solution. Okay, so that would be the first example of doing a cross-section. Okay, so I'll move on now to the second page, and we'll do another similar example to this. Okay, so this time I've got a picture of the region that I'm going to be looking at. This time it's going to be looking at y equals cosine of x. Okay, so that's the function that's going to be represented by this curve right here, y equals cosine x. And then I'm giving you, see, this is the positive x-axis, and that's the positive y-axis like that. So it tells me that I'm going to be integrating from negative pi over 2, okay, 2 pi over 2. Now I'm not, and then that's a point with an x-intercept, so that's the x-intercept, negative pi over 2, 0, to the point positive pi over 2, 0, like that. So they're given this time. Okay, so this time they're saying we have an isosceles right triangle. And isosceles right triangle means these sides are congruent. So that side right there is going to be congruent to that side right there. And we're going to be integrating from this x value right here to this x value right there. So that's how we're going to set up our integrals. We're going to be integrating in that direction right there. Okay, so the first thing we got to do is we got to figure out our area function for our triangle. So basically what you have is you need to figure out what that distance right there is, and then this distance right here, since it's an isosceles, they're going to be the same length. Okay, so this is just going to be given from the distance between the y value on the curve and 0. So that means that distance right there is just going to be y equals square root of cosine x. Okay, and what you're really doing is you're doing cosine of x square root minus 0, so you just get cosine of x. So what we end up getting is these two sides are going to be given by the function. Okay, so this side is going to be square root of cosine x. This side right here is also going to be square root of cosine x. Again, this is an isosceles right triangle, so the sides are equal to each other. So what we would get is our area function that we're interested in integrating is just going to be, on a triangle, remember that's 1/2 the base times the height. Now since this is an isosceles right triangle, the base and height are the same thing. Okay, so you're going to get 1/2. The base is going to be square root of cosine x. The height is also going to be square root of cosine x. So if you work that out, you get 1/2 square root of cosine squared x. And then that's going to just end up giving us with an area of 1/2 cosine x. So that's what we're going to integrate. So that's step 1, is really figure out what your area function is. And then step 2, we're going to go through and do the integral. So when we set up the integral for our volume, we're going to have the integral, and again we're going from negative pi over 2 to pi over 2 of the area function times dx. Okay, and dx, what that really represents is that, not the hypotenuse, but how wide that piece is. We're making the triangles get infinitely skinny. Okay, that's the idea. So our integral that we're going to do is going to be the integral from negative pi over 2 to pi over 2, and then the function we're integrating is 1/2 cosine x times dx. So again, that's the area of the triangle, and that thing right there is kind of like the depth of the triangle, because we're making a volume out of that, and it's infinitesimally small. Okay, so we're ready to now do our integral. I'm going to take the constant of integration out like I'm used to doing. So I have 1/2 times the integral of cosine x times dx, integrating from negative pi over 2 to pi over 2. Okay, so we're now ready really just to get the antiderivative. So I'm going to write down the 1/2. And remember, if you're doing an integral of a cosine, what do you differentiate that gives a cosine? That's going to be a sine. So that's going to be 1/2 the sine of x, and you're going to integrate from negative pi over 2 to pi over 2 like that. Now you're ready to use the fundamental theorem now. So we got 1/2. I'm going to draw a bracket, and then we're going to do the upper limit, just evaluate the pi over 2 in. So we're going to have sine of pi over 2 minus, and then the lower limit goes in, so we're going to have sine of negative pi over 2 like that. and we just work out the details. Now, in terms of a unit circle, remember, if you have a unit circle popping up like I do on this, so if I drew, you can do this in your head. I'm just kind of reminding you that in a unit circle, at pi over 2, which is the positive y-axis, you have the point 0, 1. And at negative pi over 2 on a unit circle, you have the point 0, negative 1. Okay, recalling that the sign is the y value, that will give us the values we need. So we're going to have 1/2. The sine of pi over 2 is 1. The sine of negative pi over 2 is negative 1. So we're going to have the volume is 1/2 of 1 plus 1. So that is 1/2 times 2. So that's equal to 1. So that's kind of a nice, simple, elegant answer on that. That area is going to be equal to 1. So that's your solution for that one right there. Okay? So that's the idea of what you're doing on the general slicing method. Now, one thing I want to remind you of a little bit, I'll pull my calculator up here. Now, you have to assume that your integral's right. If you look at this integral, we can check that integral actually on our graphing calculator. We could go, we want to make sure that we're in radian mode, of course, and then we could just graph the cosine of x, okay, like this. And then for a window, we're integrating from negative pi over 2 to pi over 2. So I can put in negative pi over 2, and then I can put in pi over 2, like that. And it doesn't matter what the scale is, really. I could scale by whatever I want to. If I want to scale by pi over 2, that's okay. Or you can even just leave that alone because it doesn't make that much difference. And then negative 2 to 2 is a pretty reasonable scale on this one. Or negative 1 to 1. And then we can graph that. And then what we're really doing is we're looking at this area of that region right there. So if I go second trace, option 7, the lower limit's going to be negative pi over 2. That's the lower limit of my integration. Okay, so I want to put in the pi over 2. So I'll go negative pi and over 2. That will be my lower limit. Upper limit will be positive pi over 2. Okay, and put that in, and that will shade that region then. Now remember, we're doing half of this integral, so this should give you an area of 2, it looks like. Okay. All right, so notice that's 2 right there. So that's giving your answer of 2. Half of 2 is going to be 1, so that verifies it for us. So don't forget, your graphing calculator is a great way to verify the values of your integrals then. Okay? Okay, now I'm going to go to second page, and on the second page, we're going to do a third slicing example here. This time, what we have is, I've kind of written it out like this. This is the positive x-axis, that's the negative x-axis. That's positive y, that's negative y, like this. So what we're going to be doing is we have two curves. We have a curve that looks like it's the top curve. I'll label that as the top curve. Then we have the bottom curve, which is y equals x squared, and I'll label that as the curve on the bottom. That's important when you're finding area between two curves. And we have semicircles. So if you kind of look in here, I'll just kind of use a dashed line to represent the semicircles. That's the center right there. So that's the cross section that we're going to be doing. And these semicircles are going from left to right. So we're going to integrate from left to right, and we need to figure out these two intersection points right here. We need to figure out just the x values too, because we're going to integrate from left to right and make an integral with respect to x. So step one in this problem is going to be, we need to really find the intersection points. So I'll kind of label the steps as we go. So we're going to find the the points of intersection. And we're going to do that by setting the two curves equal to each other. We're really just solving a system of equations. So what I'm going to do is I've got just set x squared equal to 2 minus x squared. That's going to be a pretty standard quadratic equation. So what I'm going to do is just, you can move this, or you're really just adding x squared to both sides. Okay, when you do that, you're going to get 2x to the second is equal to 2. And then I can divide by 2. So I get x to the second equals 1. Then I can square root both sides. So I get x equals plus or minus 1. So that means that this x value is negative 1. That x value right there is 1. Now, if you did want to find the y value, all you do is just do x squared, because y is x squared. So you would get 1 squared would be 1, so that would give that. And over here you would have y equals x squared. So that's going to be y equals negative 1 squared. So that's going to be 1 like that. So that would be step 1, is to go ahead and get our intersection points. Step 2, we need to really find the area function. And we're going to find that with respect to x. So this is a semicircle. That's what your focus is how do you find the area of a semicircle. So the area of a circle is pi r squared. So the area of a semicircle would be half of that. So it would be 1/2 pi r squared. So what you have to do in this problem is, the key thing is you got to figure out what the radius is. So you want to look at your diagram and see if you can reason that out. Well, the idea is the radius would be half of that diameter right there. Okay? Now the diameter, if you want to find the diameter, what you're really doing is you're taking this y value, I'll call that like y2, and I'll call that y1. So you're subtracting those two. It's the distance between those two. So what you would end up having on this for your radius, and I'm going to move this up just a slight bit here and kind of go over to the side, because really we got to figure out the radius. Okay, and what that's going to be is it's going to be half the distance. And I'm going to write this down. It's going to be half the distance from y2 to y1. Okay, so what that's really giving you is it's going to be 1/2 the difference, okay, of the upper curve, okay, which would be 2 minus x squared. Okay, that's the curve that's on top right there. So if you look at your diagram in here, the curve that's on top is this one right there. And then the curve that's on the bottom is the quadratic x squared. So it's the difference between those two. So you'd have 2 minus x squared minus x squared is the radius, and then we can clean that up, and that's 1/2 2 minus x squared minus x squared. So that's going to be 1/2 of 2 minus 2x squared. Well, I could factor a 2 out to get 1/2 times 2 times 1 minus x squared. That'll divide out the 2's to give you a radius. So that radius is going to be just 1 minus x squared. So that's what's going to plug in right there. So I'm going to take that and plug it in there. Then I've got my area function built. So I've got the area is 1/2 pi. The radius is 1 minus x squared squared. So that's going to be what we're going to integrate then in our integral then, like that. So you got to think about that a little bit. It's half the distance. And see what's happening. If you look at your diagram, that's your diameter right there. Your diameter is a distance between the y values. Therefore, the radius is half of the diameter, so that's how that's going to go. Okay? Now we're ready in step 3 to go ahead and set up our integral now. Okay? So I'm going to go ahead and get that set up. So step 3, let's set up our integral. And what we'll do on this is we're finding a volume now. So we're going to integrate from, okay, look at your limits of integration. Okay, we got from -1 to 1. So that's going to be how we're going to integrate. negative 1 to 1. And then we're going to be integrating this area of a semicircle, that area function, that's representing the semicircle, times dx. Okay, so that would be the semicircle's area. Okay, and then this would be the thickness, kind of going into the third dimension, and that's infinitesimally small. So what you have is a semicircle of infinitesimally small dimensions like that. Okay, and then to go ahead and get this set up before we do the calculus and do the integral on this, we're going to have the integral from negative 1 to 1. Our semicircle's area was this, so we're going to have 1/2 pi times 1 minus x squared times dx. Okay, so that's what we have. That's what we're going to do to get our final volume, is we're going to integrate that. Okay, now I'm going to move this down a little bit. Now the rest of our focus on this problem is going to be simply going through and working out that integral now. Okay, all right, so step 4, we'll go ahead and work out the integral. All right, so I'm going to do the integral, negative 1 to 1, and while I'm at it, I might as well go ahead and just take the constants out. So 1/2 pi is a constant that can come out of the integration. So we have integral negative 1 to 1. I can go ahead and I can square that. Okay, so I can just do that. That would be 1 minus 2x squared plus x to the 4th times dx. And that's going to be a pretty simple power rule integral. So we're going to have, when we do this, let's see, we'll have 1/2 pi. Our antiderivative is going to be x minus 2x to the 3rd over 3 plus x to the 5th over 5. And we're going to be integrating that from negative 1 to 1. Okay, so that's the antiderivative. Now we're going to use Fundamental Theorem to work this out. So I'll go ahead and get that done here. So we got 1/2 pi. Plug in the 1. We're going to have 1 minus 2 times 1 to the 3rd over 3 plus 1 to the 5th over 5. And then subtract the lower limit, which would be negative 1 minus 2 times negative 1 to the 3rd over 3 plus negative 1 to the 5th over 5, like that. And then that will be the arithmetic that we'll work on. Okay, so wrapping up the details here, we're going to have 1/2 pi. Okay, if we look at this arithmetic there, and then we're going to look at this arithmetic, you've got to be pretty careful with your arithmetic steps. Looks like we're going to have 1 minus 2/3 plus 1/5 minus, and then be careful you have negative 1. And then this is going to be negative, and I'll go ahead and write this step, that's negative 2 times negative 1/3 plus negative 1/5 over 5. You're taking a negative number and you're raising it to an odd power. So that's going to be 1/2 pi. And this will be 1 minus 2/3 plus 1/5 minus negative 1 plus 2/3 and minus 1/5. Now we're getting pretty close to wrapping this thing up then. Okay, so from here I'll write this as 1/2 pi, and we're going to have 1 minus 2/3 plus 1/5 plus 1 minus 2/3 plus 1/5, changing the signs. What I just did there was distributed the negative. Okay, now let's collect like terms and put this together. So I'm kind of running out of room here, so I'm going to go 1/2 pi. Okay, and inside here I've got 1 plus 1 is 2. And then I got negative 2/3 minus negative 2/3 is negative 4/3. And then I've got 1/5 plus 1/5 is plus 2/5. So now I'm going to need to get common denominators. So that's going to be 1/2 pi. Common denominator is going to be 15. So the 2 turns into 30 over 15. Okay, this one, you're going to have to multiply this one by 5 over 5 to get 20/15ths. Okay, then the 2/5, we're going to convert that by multiplying that by 3 over 3. So that's going to be 6 over 15. Okay, so it looks like we have 1/2 pi. And then this is going to be 10. That's going to be 16/15. So when you multiply that straight across, you're going to get 16 pi over 30. And then we can divide this by 2 to get a final answer, which appears to be 8 pi over 15. And that will solve the problem for us then. A lot of work. So 8 pi over 15 should be that exact volume under that curve then, assuming I've got all my arithmetic right. Okay? Okay, now again, so I'm going to pull up the calculator and I'm going to double check the integral that I just did. I'm going to move this kind of over the side here. And what I'm going to be looking at is this integral right here. So I'm going to go ahead. You know, you can get the whole answer like this. You can go ahead and put in the 1/2, because what you can go ahead, you got to put this in like this if you want to. You could go, let's just go 0.5 pi for the 1/2 like that. Then we'll put in 1 minus x squared, close the parentheses and square. So that's really what we're integrating. And we're integrating from -1 to 1. We just need to get a picture of that graph, and then we can estimate the answer on that and make sure we did that right. So for the window, I'm going to go from -1 to 1, because that's what the limits of integration are. And we can scale by 1. As far as we can try -2 to 2 and just see if we get a picture. Okay, so that's pretty good. Now I'm going to go second trace, option 7, and I'm going to integrate from -1 to 1, like the integral we just did. Upper limit's 1. It should shade the region. And then we'll see if that's the decimal approximation of 8 pi over 5. Okay, so this is giving 1.6755161. So now if I just clear this, and if I take my calculator and go 8 pi and divide that by 15, I get the same thing. Okay, off a little bit maybe, but that looks really accurate actually on that. So that looks like we got a good answer on that problem then. Okay, so that's how that would go. That's 3 good examples. So I'm going to go ahead and stop this recording here. And we're going to kind of do 3 recordings on this section. This gives you 3 really good examples of the slicing method. And that'll wrap us up. All right, hope that helps.